Hello everyone, welcome to Gradeup. My name is Shantanu Sanwal and today we are going to do or solve the previous year problems on the principal stresses, Mohr circle and theories of elastic failure. Okay, so let us begin. First of all, let me tell you about the complete free online GATE ME course that is ongoing on our Gradeup platform. Okay, this course has been designed by the GATE toppers and the experienced faculties. Okay, it has got a complete study plan of 90 days. This course started from 18th of September and this course is ongoing. Okay, though already some days have passed, okay, a few time has passed, but still there is lot of time left for your exam, GATE examination that is going to held in the month of February. So still you have a plenty of time left. So you can still go to the link is given in the description box. You can go to that link, click on the link, subscribe to this course and start learning and boost your preparation for GATE 2019. Okay, this course contains 200 plus video lectures and 250 plus quizzes for all the topics, and we are also conducting the live doubt session, the live quiz sessions for this course. All the subjects which are ongoing on the course, we are conducting the live sessions also on these topics. Okay, so let us start with the question number 1 asked in GATE 2015 set 2. Okay, we will read the question. What does it say? The question says the uniaxial yield stress of a material is 300 megapascal. Okay, it is the uniaxial state of stress, and then it is saying according to von Mises criterion. The von Mises criterion is the theory of failure, the fifth theory of failure. Okay, that is the MDET, maximum distortion energy theory. Okay, the shear yield stress in megapascal of the material is. It is asking about the shear yield stress, and the uniaxial yield stress of a material is given as 300. Okay, so it's a very simple question. Just you have to apply the basics of the von Mises or the MDET, that tau according to von Mises, okay, according to von Mises criteria or the MDET, that is maximum distortion energy theory, tau is equal to SYT by root 3. Okay, so SYT is, this is the SYT value because this is the uniaxial yield stress. So this is 300 divided by root 3. So you will get this value as 173.1 megapascal, because this is also given in megapascal. So this will also come in megapascal only. Okay, so this is just the answer for this, that is 173.1. This was an NAT problem asked in GATE 2015 set 2. Okay, this is a very easy problem. I don't think any further explanation or clarification is required in this question. Okay, so let us move to the next question.
Subscribe to our channel and press the bell icon to never miss any update from Gradeup.
This is again the question asked in the same set in the same year 2015 set 2. Let us read this question. In a plane stress condition means it's a 2D problem. Okay, this we have discussed. The components of stress at a point are 20 megapascal. Okay, this is sigma x equal to 20 megapascal, sigma y is equal to 80 megapascal, and tau xy equal to 40 megapascal. Okay, these are the values, that this is sigma x, this is sigma y, and this is tau xy. Okay, so the maximum shear stress in megapascal at that point. It is asking about the maximum shear stress. So we will use the second theory of failure, that is the Mssd, maximum shear stress theory, also known as the Guest and Tresca's theory. The Guest and Tresca's theory. So we have to find out the maximum shear stress at this point. So according to this theory, what is the criterion for safe design? That is absolute tau max must be less than equal to SYS, that is the yield stress in shear, divided by the factor of safety. Okay, since we are not given anything about the factor of safety, okay, but we have to find out, yes, we have to find out the absolute tau max only, because this is the basic condition, but we do not have these things to find out. Okay, we just have to find out the maximum shear stress. So absolute tau max, the expression for this absolute tau max is equal to larger of sigma 1 minus sigma 2 by 2, comma sigma 2 minus sigma 3 by 2, comma sigma 3 minus sigma 1 by 2. Okay, the larger of them. But the thing in this case, first of all, it's a 2D problem, so this sigma 3 term will be cancelled. Okay, then sigma 1 and sigma 2 are to be found out, because in this sigma 1 and sigma 2 are not given, but sigma x and sigma y and tau xy are given. So first of all, finding out the sigma 1 and sigma 2, okay, simply 1 by 2 sigma x plus sigma y plus minus root of sigma x minus sigma y whole square plus 4 tau xy square. Okay, just substitute the values of sigma x, sigma y and tau xy. We will get the values of sigma 1 as 100 and sigma 2 as 0. Okay, these are the values what we will get. Just substitute sigma x equal to 20 and sigma y equal to 80 and tau xy equal to 40. Okay, then finding this expression, that is the absolute tau max, must be larger of sigma 1 minus sigma 2, that is 100 minus 0 divided by 2, comma sigma 2 by 2, that is 0, comma minus sigma 1, okay, minus sigma 1 by 2. Okay, so this will come as larger of 50, comma 0, comma 50. So the larger value is, either you can take this and you can take this. So the larger of these will be 50, and we are dealing in megapascal, so the units of this will also be megapascal. So the correct answer for this option, the correct option for this question is option C. That is the absolute or the maximum shear stress in megapascal at that point is nothing but 50 megapascal. Okay, simple problem. Just we have to find out the absolute tau max, first cancelling the sigma 3 because it is a plane stress problem, so the stress in third direction will be 0. That is the basic understanding. Then just finding the absolute tau max, and for that we require sigma 1 and sigma 2, the principal stresses, that is the major principal stress and the minor principal stress, and so just finding that by using the simple expression. Okay, and then just substituting the values and getting the values of absolute tau max or the maximum shear stress theory. Okay, next, if factor of safety would have been asked, if the question would have been a variance, there could have been a variance in this question, that if n could be asked, n means factor of safety. So if factor of safety would have been asked, then this SYS value would have been given. Okay, we will see that kind of question also. If it has been asked any question of that sort also, then also we will look at finding the factor of safety. Okay, so let us move. Next question, GATE 2016 set 1. This is the principal stresses at a point inside a solid object are. These are the principal stresses that are given, that is sigma 1, sigma 2 and sigma 3. See, sigma 3 is equal to 0, that means it's again a plane stress problem or a 2D problem. Okay, plane stress problem or 2D. Next, the yield strength of the material is 200 megapascal. The yield strength has been given as 200 megapascal. The factor of safety calculated using Tresca, that is maximum shear stress theory, is this, that is the second theory, Mssd, Tresca, Guest and Tresca. Okay, and the factor of safety calculated using von Mises is the last one, that is the MDET, maximum distortional energy, is epsilon. This is eta. Okay, what is this? Nu. What is this? Eta. Okay, V, and this is T. So which one of the following relations is true? We have to find out which of the following relations is true. So first of all, we have to find out the factor of safety using both the theories, that is the Mssd and MDET, and then we will see the relation, what the relation actually comes. Okay, so let us do this. Sigma 1 equal to 100 given, sigma 2 is also 100. Okay, and we are not concerned with sigma 3 since it is equal to 0. Then according to Mssd, we know that larger of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2 and sigma 3 minus sigma 1 by 2 must be less than equal to SYS by n. Okay, so just using that, 100 minus 100 by 2 is 0, 100 minus 0 by 2 is 50, comma 100 minus 0 is again 50. So the larger of these value, larger of these must be less than equal to SYS by n. Okay, or this SYS, this is the yield strength is given, so this will become, this is SYT, so this will become SYT by 2n, because SYS, yield stress in shear, is equal to SYT by 2. This also we know. Okay, then the larger of all these will be equal to 50. So taking the limiting value, just equating it equal to SYT, that is 200 divided by 2 into n. So cancelling out this from here, we get n equal to, that is the factor of safety according to the Tresca's theory, equal to 100 by 50, which is equal to 2. Okay, so we just write it down here, that is, this is equal to 2. Now using the next theory, that is the MDET, maximum distortional energy theory. What does that theory says? Okay, that theory says that sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square must be less than equal to twice of SYT by n whole square. Okay, since again in this case the sigma 3 is equal to 0, so just cancelling out them. So we are left with sigma 1 minus sigma 2 by whole square, so that will be 100 minus 100 whole square will be 0, plus 100 whole square and plus 100 whole square, and taking the limiting value, just equating it, equal to 200 by n whole square. Okay, so this will become 2 into 100 whole square equal to 2 into SYT by n whole square. So this 2 and 2 goes cancelled, taking the root on both sides, we are left with 100 equal to SYT by n, or this n becomes equal to this is equal to 200. Okay, so this will become 200 by 100, which is equal to 2, or this is according to von Mises equal to 2. So we have seen according to the Tresca's theory also equal to, it is equal to 2, the factor of safety, and according to the von Mises also it is equal to 2. So the relation that holds correct is, that is, both the factor of safety according to the Tresca's theory and also according to the von Mises theory are equal. Okay, so the option C is correct for this problem. Okay, simple problems, just you need to remember the basic expressions, the conditions for safe design. Okay, that is only the equations that will be used throughout this chapter of theories of failure, and most of the questions are asked from the whole set what we are doing right now, that is the theories of failure, the Mohr circle and principal stress strain. They are actually all are related to each other, but most of the problems, the practical problems, the questions that are really asked in the examination, especially the gate examination, are generally from the theories of failure part. Okay, so you have to be much focused on this topic. Just you have to remember all the equations, just one equations you have to remember, and also you have to remember the conditions that which theory of failure is suitable for which case. Okay, that we have discussed in the course, that we have discussed in the video course, for which I told you about in the first slide, that there are few the course is there. Okay, so you have to subscribe to that course and see all these things out there. We have discussed this in the course also. Okay, now let us see the next question, asked in 2016 set 2. A machine element xy, this is the machine element xy, fixed at the end x, this is fixed at x end. Okay, is subjected to an axial load P, this is subjected to an axial tensile load P, transverse load F, okay, and a twisting moment T at its free end y. At the free end, these are the things that are acting, that is the transverse load F, the twisting moment T, and the axial load P. Then it is asking the most critical point from the strength point of view is. The most critical point, so first of all you have to understand that what is a critical point. The critical point is the point on the critical cross section at which the stresses induced are maximum. Okay, and the critical cross section is that cross section on which the stresses are maximum. Then on that cross section also there will be one point where the stresses are actually the maximum, and that point is known as a critical point. Okay, so we will see, first of all, due to this axial load P, there will be the compressive stress, and that compressive stress will be same at all the cross sections. Okay, they will simply be like this, its distribution will be simply shown like this, and they will be same at each and every cross section, whether you take the cross section here, here or here, anywhere. If you take from the free end till the free fixed end, the cross section at each and every cross section, the compressive stresses, the tensile stresses, sorry, will be the same at each and every cross section. So from that we cannot find out which point is the critical point. Let us see next. That is, this force, the transverse shear load, will cause the bending moment. Okay, will cause the bending moment, because if you take any section, suppose this is the section XX we are considering, so the bending moment at this will be equal to minus F into X, and we know that the stresses, that is the bending stress, is equal to by Z, where Z is the section modulus. This is the section modulus. This is section modulus. Okay, this mxx is nothing but minus F into X. So as you can see, this bending stress varies linearly with X, and if we are considering the value of X from this fixed end, so at this point, that is at Y, the X is equal to 0, so the stress induced will be 0, the bending stress induced will be 0 at point X, Y, or the free end, and at the X, that is at the fixed end, the stresses induced will be maximum. Okay, so, and the bending stresses are shown like this. Okay, they are shown like this in this plane only, the plane which is lying perpendicular to the plane of cross section, or the plane which is lying parallel to the line longitudinal axis. Okay, so according to this we are getting one hint that Y cannot be the critical cross section, or any point on the Y cannot be the critical point. Okay, because the bending stresses are 0, so the effect of bending stresses are almost nullified, totally nullified at the point at the Y cross section. So we can right now here only cancel out these two options, that these two options can't be correct, that is option A and option B cannot be correct. By this much only we have understood this. Now talking about the effect of torsion, that is T, what does this shows? The shear stress induced due to torsion is given by 16 T by pi d cube. Okay, and this is the case of pure torsion. So the torsion induced, or the shear stress induced due to this torsion, will be same at each and every cross section, and the torsional shear stress distribution is shown on a plane like this. It is shown on a plane which is perpendicular to the longitudinal axis and parallel to the plane of cross section. So the shear stress induced due to this torsion will be same at each and every cross section. Then the stresses, the axial stress developed due to the tensile load P, that will also be the same or equal at each and every cross section. But only thing that will decide whether the critical cross section will be at X or at Y, or in some way in mid between the free end and the fixed end, that will depend upon the shear load. Okay, that is causing the bending moment. So as I have told you that this is linearly depending with X, so X is maximum at the fixed end, so the critical cross section will be X. Okay, that won't be any way in between, and that is also what is saying that at location X, at location X. But now we have to find out that whether it will be on the circumference or will be at the center. But as I have shown you here in the distribution, this is the center, that is the longitudinal axis is passing through it like this. So at the center, the effect of bending stress is 0, of the bending moment, or the bending stress that is induced at the cross section or the center of the cross section is 0. Okay, so at the circumference it is maximum. So the stresses also will be induced maximum at the circumference only, and that too at the fixed end. So the correct option will be a point on the circumference at location X. Okay, this was a theoretical problem that just checked your knowledge about whether you know that what is the stresses that are induced due to the shear force which causes the bending moment eventually, the torsion which causes the shear stress, and the load, axial load, which causes the axial stress, and what is the nature of their distribution, that whether they are each same at each and every cross section, and from the center to the means what is their radial distribution also, not only the axial distribution but also the radial distribution, that whether they are same at each and every point in a cross section if you take it at any cross section. Okay, so that this question just check the basic knowledge of how all these stresses are induced and what is their distribution. So this is a theoretical question, a very good question I must say. Okay, so you have to focus on such theory parts also, or such conceptual parts also, that where all these things are acting. Okay, so let us move forward. Let us see the next question. What does the next question says? The next question is question asked in GATE 2016 set 3. Okay, this is a square plate of dimensions L cross L is subjected to a uniform pressure load P equal to 250 megapascal on its edges as shown in the figure. Okay, assume plane stress conditions. The Young modulus is equal to E is equal to 200 gigapascal. So the deformed shape is a square of dimension, the deformed shape, because from external the load is acting or the pressure acting, so it will compress a bit. So the deformed shape of the is a square of dimension L minus 2 delta, because delta is decreasing from all these sides, so this will become L minus 2 delta. If L is equal to 2 meter and delta is equal to 0.001 meter, then the Poisson ratio of the plate material is. It is asking the Poisson ratio of the plate material. Okay, so let us see what we can do for this problem, how to solve it. We know from the expressions we have read that epsilon x is equal to 1 by E sigma x minus mu sigma y. Okay, or epsilon x is nothing but delta L, that is the change of length or dimension on x direction. Okay, so this will be, because the dimension that is changing is delta L by L, or simply you can write it as, because this is 2 delta upon L, okay, equal to 1 by E sigma x minus mu sigma y. Okay, then you can see sigma x and sigma mu, sigma x and sigma y are same, so they can be taken out because there is the pressure that is acting on both the sides. So this will be 2 into delta value is given as 0.001 divided by L is again, L is 2 only. This will be equal to sigma x or sigma y by E, that is the value is 250 megapascal. Then E, but you have to convert this, E is given as gigapascal, so you have to convert it into megapascal into 10 to the power 3 and 1 minus mu. Okay, so these two get cancelled. If you remove this, the 1000 will come here and this goes off. So we are left with 1 minus mu is equal to 200 divided by 250, which is nothing but 4 by 5 or equal to 0.8. So on substituting this or on solving this, we will get mu is equal to 1 minus 0.8, which is equal to 0.2. Okay, very easy problem. Just using a simple expression, the basic expression for strain in one direction and finding out the value of Poisson's ratio. Okay, next question, GATE 2017 set 1. Okay, please focus on this question. This is a really good question. A rectangular region in a solid is in a state of plane strain. Okay, plane strain again means a 2D case. The xy coordinates of the corners of the undeformed rectangle are given by P at 0, 0, Q at 4, 0, R at 4, 3 and S at 0, 3. Okay, this is not a square, this is a rectangular region. Okay, because in one direction the dimensions are 4 and the other directions the dimensions are 3. Okay, then the rectangle is subjected to uniform strains, that is in the x direction like this, in the y direction like this, and these are the shear strains. These are the normal strains and these are the shear strains. Then the deformed length of the elongated diagonal up to 3 decimal places is, okay, let us see this. First of all, just try to draw the rectangle, that is P 0, 0, Q 4, 0, R 4, 3 and S 4, 0, 3. Okay, this is the rectangle. Then in this rectangle there will be a diagonal like this, suppose, and since the strains are acting in the x direction and in the y direction, so first of all we have to find out this length of this diagonal, that what is the undeformed length of this diagonal. Okay, the undeformed length of diagonal will be equal to, this is 4, this is 3, so this will be 4 square plus 3 square root, using the Pythagoras theorem, that will be 5. So this will be 5 units. Okay, simple. Then this is the undeformed length. Then we have to find out the elongation in this direction. Okay, so for finding out the elongation, we have to find epsilon n at this plane. But what is the angle of this plane from the x-axis? At theta, and that theta we have to find out. First of all, we will find this angle. This angle will be tan inverse 3 by 4. Okay, and if you find out this tan inverse 3 by 4, you will get the value as 36.87 degrees. Okay, then we have to find the value and the value of theta, the complete theta of this plane from the x-axis. Okay, so this plane or this plane is the same plane, but you know one thing, that we take in the normal strain equation or in the normal stress equation, finding on an oblique plane, we take the value of angle or the value of theta from the x face, and that too in a clockwise direction. Okay, so that means we can take this value. Okay, so this value total will be equal to, first of all, this and this will be same, these two will be same. Okay, then we have to find these two values. So this value will be, or we can say this value, just add this, because this angle is 180, remove this, this angle is 180 and this angle is same, so just adding this value we will get the value of theta as 180 degree plus 36.87 degrees, which will be equal to 216.87 degrees, that is theta. So we have to find out the epsilon n, that is the normal strain at an angle of theta, at an oblique plane, that is at an angle of theta, that is 216.87 degrees. So simply we know the formula or the expression, that is sigma n equal to 1 by 2 sigma, not sigma, epsilon n, epsilon xx plus epsilon yy plus 1 by 2 epsilon xx minus epsilon yy cos 2 theta plus gamma xy by 2 sin 2 theta. Okay, so just substituting these values, all the values have been given, just substitute these values, you will get the epsilon n as, the values of epsilon n will come as 2.8 into 10 to the power minus 3. But this is the strain. We have to find out the length. The strain is the change in dimension upon the original dimension. So the elongation will be given as original dimension multiplied by the value of a strain, and this you will get as 0.014. So this is the elongation, and the original length was 5. So it is asking you the deformed length. So the deformed length will be equal to 5 plus 0.014, that is equal to 5.014 units. So the answer is 5.014 units. Okay, this is also a very good question. Just simply you have to find out the angle and the normal strain in that direction, and then you can find out the deformed length of the diagonal. Okay, then the next question, GATE 2017 set 2. The state of stress at a point R, sigma x, sigma y, sigma z, tau xz, tau zx, tau yz, tau zy equal to 0, and only tau xy and tau xyx exists, that is equal to 50 megapascal. So it is asking the maximum normal stress in megapascal at that point. Okay, so this will be what it will be. First of all, it's a case of pure torsion. You can know that this is the case of a pure torsion. Okay, but first of all, let me draw the state of stress for this point. Only tau xy and tau yx are acting on this plane like this. That is also 50 megapascal. Sorry, let it right here. 50 megapascal on this side and 50 megapascal on this side. Okay, this is positive. So if we will solve this problem by a Mohr circle case. Let us see. A, if we say the state of stress or on the x phase, that will be 0, 50, and if we talk about the B, that will be 0, minus 50. Okay, this I have told you how we find out in the Mohr circles chapter. So that now just drawing the Mohr circle for this case, first of all writing the coordinates tau and minus tau. So A point will be at 0, 50 and B point will be at 0, minus 50, 0, minus 50. So the center of this will lie at the origin, and just you have to draw the circle. This is the Mohr circle. Then it is asking the maximum normal stress in megapascal at that point. So the maximum normal stresses, we know that there will be two stresses, one will be positive and one will be negative, that this will be sigma 1 equal to 50 megapascal and sigma 2 will be equal to also 50, but it will be minus 50 because it will be compressive in nature. Okay, so it is asking the maximum normal stress. So the maximum normal stress will be equal to 50 megapascal. Already it is asking megapascal, so just write the answer as 50. Okay, very easy problem. Just we have seen also the the use of Mohr circles, how to use the Mohr circle to find out the values of stresses. The next question, again GATE 2017 set 2. The principal stresses at a point in a critical section of the machine component are. This is sigma 1, sigma 2 and sigma 3. These are the three principal stresses that have been given to you. For the material of the component, the tensile yield stress is this. According to the maximum shear stress theory, the factor of safety is, again very easy problem. Just you have to find out the absolute tau max and equate it to SY S by N, and you will get the value of the factor of safety. Okay, just doing that again, larger of 1 minus 2, that is 55 by 2, comma 2 minus 3, that is 45 by 2, and 1 minus 3, that is 100 by 2, will be 50, equal to SYS by N. But this is given the yield strength, the tensile yield strength. So this will be SYT is given. This is SYT, that is SYT is equal to 200. So just using that SYT by 2N. So this will be the larger of all these will be 50. So 50 equal to 200 divided by 2 into N. So getting this cancel, which implies N equal to 100 divided by 50, which is equal to 2. So the factor of safety according to the Mssd or the Gaston-Tresca's theory is equal to 2. The correct option is option B, that is factor of safety is 2. Okay, let us see the next problem, the last one, GATE 2018 set 1. The state of stress at a point for a body in a plane stress is shown in the figure below. Okay, if the maximum principal stress is this, then the normal stress sigma y in kilopascal is. This is also given in kilopascals and also asked in kilopascals, so there is no change in the dimensions or change in the units. Okay, so it is saying the maximum principal stress is given as this. This is sigma 1 is equal to 10, and the value of sigma x you can find out from here 100, and sigma y not given. Sigma y we have to find out. and tau xy has been given as minus 50, because you have to remember the sign conventions that the stress on x phase, if it is in the clockwise then it is positive, if it is in anti-clockwise then it is negative. So this is negative. Okay, so just solving this, what we can get, sigma 1, we have to find out sigma 1, that is equal to 1 by x. Okay, no, sorry, this is asking thing the minimum, so this will be sigma 2, not sigma 1. Okay, sigma 2, because this is saying the minimum. Okay, then this will be sigma x plus sigma y. For finding the minimum, we have to use a minus sign here, otherwise for sigma 1 and sigma 2 there is plus and minus both, but we are talking about the minimum, so there will be minus. Then root of sigma x minus sigma y whole square plus 4 tau xy square. Okay, so just substitute the value, sigma 2 equal to 10, 10 equal to 1 by 2, x is 100 minus sigma y minus sigma 100 minus sigma y whole square plus 4 into minus 50 square. Okay, so this you will get as 20 equal to 100 minus sigma y minus 100 minus sigma y whole square plus this will be 2500 into 4, that is 10,000. Okay, so just taking these values here and these them that side, 100 minus sigma y whole square plus 10,000 is equal to 100 minus 20 will be 80 minus sigma y. So just squaring both sides, we will get 100 minus sigma y whole square plus 10,000 is equal to 80 minus sigma y square. So just now simplifying it, 10,000 plus sigma y square minus 200 sigma y plus 10,000 equal to 80, that is 6400 plus sigma y square minus 160 sigma y. So this sigma y square gets cancelled. We are left with 200, sorry, this will be plus out here rather, plus, so this will become plus. Okay, so 10,000 plus 10,000 is 20,000, 20,000 minus 6400 is 13,600 is equal to 200 plus 160, that is 360 sigma y. So just solving this, we get sigma y equal to 13600 divided by 360. So on solving this, you will get the answer as 37.38 kilopascal, and the correct option for this is option number C. Okay, so if you have any comments, any doubts, you can write to us on the comment section given below. Press the like button, share this video with your friend, and also subscribe to the channel so that you can get many more awesome videos like this. So see you in the next class with the topic of SFD and BMD. Till then, keep learning, keep growing. Thank you.